All right, last section in chapter 17, we're going to be dealing more with equilibrium concentrations again, but this time we're going to be dealing with solubility products. So let's look at this equation here. We have barium sulfate as a solid. It dissolves in water. You're going to get two ions, the barium ion and the sulfate ion. What's our equilibrium constant or equation for this? Think about it, you don't include solids, so your equilibrium equation is going to be Ba plus 2 times SO4 minus 2. Now, since we are simply dealing with ions in solution here, we refer to this as our KSP, which is our solubility product. So our KSP is our solubility product, and this is dealing with ions that are dissolved in solution. Now, one thing not to confuse is KSP is not the same as solubility. Remember, solubility is generally expressed as a mass of solute dissolved in 1 liter, such as molarity or parts per million. So KSP and solubility are not the same. So, if we're going to look at Le Chatelier's principle here in a common ion effect, let's say I have water, but in water I already have one of these two ions dissolved in water, then I dissolve more of this. If we look at the Le Chatelier effect, what that would say is, if you have one of these ions in solution already and then dissolve this, the equilibrium will shift to the left. Why? Because you have more of your products on the right, so it'll shift to the left and it'll decrease the amount of salt. So just something to point out there. When we talk about pH and salts, if a substance has a basic anion, it will be more soluble in an acidic solution. So just something to keep in mind. Substances with acidic cations are more soluble in basic solutions, such as like hydrogen. Remember, hydrogen's an acidic ion. Metal ions can act as Lewis acids and form complex ions with Lewis bases. So just something to kind of note here, you have Lewis acids, Lewis bases in effect when we're talking about metals. So remember, in general, we are talking about hydrogen and hydroxide as our acid-base pairing. When we start talking about these complex ions, metals can act as Lewis acids or bases. But if you look at the list, it's kind of an odd list of metals. So yes, look at this list, kind of just look over it. It is a very odd list. You're looking at silver, you're looking at cadmium, a little bit of copper, nickel, and iron. So all things that can act as Lewis acids and bases. Just a couple things remaining when we talk about solubility. We can have amphoteric metal oxides and hydroxides are soluble in both strong acids and bases. Examples of such amphoteric metal oxides would be aluminum, zinc, and tin. Lastly, if we want to know a precipitate will form, if Q equals SP, the system is at equilibrium and the solution is saturated. If Q is less than Kp, we can have more dissolved. If Q is greater than Ksp, we're going to have a precipitate. So if Q is greater than Ksp, we're going to have a precipitate. If not, no precipitate. And lastly, here's kind of a chart of kind of ions that you could kind of see here. I'll blow this up a little bit. Selective precipitation of ions, kind of showing what would happen when they mix together and what salts will form and what ions will form. So you don't really need to go over this. It's just kind of there for group 1, group 2, 3, 4, and 5. How they're classified. So the big thing with section 17.3 is the KSP value. But other than that, that should conclude 17.3.